Today's speaker is Bill Hery. He's familiar to us because this is his third presentation that he graciously agreed to give us in the MIG or SMIG forum. His previous two presentations, one on blockchain in March of 2021 and Gödel's incompleteness theorem in June of 2022 were interesting and they were very well received. Bill developed a deep interest in mathematics and physical sciences in high school, which continued in college. He attended Brooklyn Poly, which is now NYU Tandon School of Engineering, starting in 1963. There he majored in math, but took all of the few computer-related courses available. There were not many of them in 1963, I guess. There he also continued through a PhD in pure math, concentrating on topology and functional analysis. After 8 years teaching math and computer science at the college level, he left academia for industry, where he developed operational research, statistical and econometric models. In 1983, he moved to Bell Labs to develop performance models of computer networks before he got involved in the architecture of special purpose computers for government applications, particularly the fault-tolerant aspects. He moved on to network architectures and information security before taking early retirement in 2001. Then he joined again the Poly Computer Science Department, focusing on security until he retired in 2014. Bill's presentation is about John von Neumann, his life in math and science. Today he's giving part one. Part two of his presentation will be given on Monday, March 13th, starting at 11 o'clock a.m. Mark your calendars, but just in case, we will send you a reminder notice about 1 week before. John von Neumann is a preeminent Hungarian American mathematician. Von Neumann is one of the prodigies that came out of Budapest, Hungary, the others being Theodor von Karman, who was a mathematician best known for something called Karman line, which is a boundary between Earth's atmosphere and the outer space. Another is Leo Szilard, who conceived nuclear chain reaction. We also have Eugene Wigner, a Nobel Prize winning theoretical physicist who contributed to the theory of atomic nucleus and elementary particles, and Edward Teller, a controversial figure known to be as father of hydrogen bomb. These five are often referred as Martians of science. There are anecdotes about the origins of this label. The essence is that there was some discussion about participants of the Manhattan Project about the smart, extraordinary Hungarian scientists. Someone suggested they had come from Mars, but to disguise themselves, they spoke Hungarian. Sounds like a first script for the Conehead movie. More recently, there were Martians from Budapest, such as Denis Gabor, the inventor of holography and Nobel Prize winner, and Peter Lux, a mathematician and Abel Prize laureate, who made important contributions to the integrable system, fluid dynamics and shock waves, physics of solids, and mathematical and scientific computing. I should point out that Bill also has some Hungarian roots, so he's in a very good company. Bill, the floor is yours.
Okay, can you set it up so I can share my, turn it over to me, or where is share screen? It was down here before.
I cannot do it because I'm not the host.
Yeah, you can share.
You can share now.
Okay. Okay. Okay, can everybody see the slides now?
Yes.
Okay, John Neumann, A Life in Math and Science, Part 1. Originally, it was going to be one session. Now it's gotten to 2 sessions. First, the blurb, which John already read, so I won't go into this. Well, actually, maybe you didn't read the blurb. Okay, he's arguably the most influential mathematician of the 20th century, having made fundamental contributions in a wide and diverse range of mathematical areas, including mathematics, physics, computer science. His work on the foundations of math, mathematics of quantum mechanics, game theory and economics, functional analysis, nuclear weapon design, computer architecture, the von Neumann architecture, nuclear weapons and energy policy is amazing, not only for its significance of his work in all these areas, but for the broad range of domains he excelled in. To give an idea of the range, if you go to Wikipedia on the von Neumann page, they start with a list of all the areas that he made significant contributions in. I'm not going to go through them. We'll touch on a few of them. What I plan to do in this talk, or the 2 talks, is go through his life and pick out a few of the areas that he made the most significant contributions and talk a little bit more depth about those. But I'll mention a lot of these, but not even all of these along the way, maybe with just one line on the slide. Before I talk about this slide, let me tell you how I got interested in von Neumann. I had John read a biography that had all the things I was doing in college and graduate school and different jobs, etc. And the main point is that every point in that, I would start looking at something new and get interested in it and find out John von Neumann had done work there. In high school, I took a book out of the library about computers because I was interested in computers, and it had the von Neumann architecture in it. And I remember that diagram. I still remember the way that looked in that book. I don't remember what the book was, who wrote it, but I remember that. I started in college and I got interested in pure math. I took a course in foundations that talked about, among other things, set theory and axiomatic set theory. Von Neumann was there. I was browsing the shelves in the college library in an area that had optimization books and things. And I found this book that was labeled game theory. I thought it was misfiled. I looked at the numbers. No, it was right. I took it out and read it and found there really is a mathematical topic called game theory that John von Neumann had invented. When I started doing things with computer architectures, there was John von Neumann. I started doing things about reliability of computers and complex systems. And he wrote a paper about building reliable systems from unreliable components. Specifically, he was thinking of tube computers where tubes could fail. How can you build things? And he included something called triple modular redundancy, where you have things going in multiple places and you vote on the solution. So you can still continue going if something fails. And this kept happening. So along the way, I started reading more about his life and his work. And John's introduction mentioned The Martians of Science. There is a book that is one of the first references I have that talks about all 5 that he mentioned. And then there are some others that should be included in there. One is Paul Erdős, who many of you probably know is the most widely published mathematician of the 20th to 21st century. He's got over 900 papers. He was close friends with the mathematicians at Bell Labs. So a lot of you should know a lot about him. Andy Grove, who was the CEO of Intel, he was actually a Hungarian. He changed his name when he came here. There's so many from that era and you know, the 50s that came over. That's amazing. Okay, everybody that met John von Neumann, who worked with him, seemed to think he was the smartest person they ever know. I put a few of the quotes here. John von Neumann, this is Feynman. John von Neumann was the greatest mathematician around. This is when he was still a grad student at Princeton. So maybe he didn't know everybody, but he certainly knew the best ones because they were attended to be at Princeton. Wigner said, there's the rest of us, and then there's Johnny. He always was Johnny in the US. He didn't want to be John or János, which was his Hungarian name. Peter Lax, good quote from Peter Lax. Hans Bethe, von Neumann's brain indicated a new species in evolution beyond man. Jacob Bronowski, I included here because some of you may remember him, even though you might not remember why. There was a TV series from BBC that was broadcast on PBS in about 1975 called The Ascent of Man. And Jacob Bernowski was the one who wrote that and directed it, etc. But he was a scientist who wanted to show how the great advance in civilization seemed to correspond to advances in science and technology. And it started with the mathematics of the Greeks and went up to the present day and included mention of John von Neumann. There's a whole section. That was another place where, by the way, I heard about John von Neumann. The series is available somewhere on YouTube, or I've been told. I haven't actually watched it. I remember I watched it when it went through. The book is available. He's a very interesting guy. It's a fascinating series. And by the way, Bernowski worked for von Neumann in England during the Second World War when he was doing operations research kind of things. Okay, so von Neumann was born in Budapest in 1903, which was actually a very cosmopolitan second capital of the Austro-Hungarian Empire. And it was moving up. It was really becoming world-class at the time, around when von Neumann was born, a little before and after, but the parliament was, at the time, was built the largest parliament building in the world. And if that's the bottom left picture, if you watch TV, you've probably seen the parliament building in all of the commercials for Viking cruises. They don't mention what it is, but that's what they keep showing. There was a new opera house. They had a subway system that was the second one in Europe after London. And it actually was the first one that was electrified. Now about his family, they came from a secular Jewish family that was very well off and well connected. Go to the building on the bottom left is the building that he grew up in. The building was owned by his grandfather, who had a business. I think he manufactured and sold farm equipment, something like that. And the first floor was for the business. The next 3 floors were for his 3 daughters and their families. So they had huge apartments. I think von Neumann's family's apartment, just for him alone and his group, had 3 brothers, or 2 brothers rather. They had something like 20 rooms. On the right, there was the plaque that is on this building. You can see it on the building in the sort of in the corner of the building. And the building next door, which was also owned by his family, has been the home of the John von Neumann Computer Society in Budapest for a long time. These pictures I took in Budapest about 8 years ago when I was passing through on a trip. But the upper classes in Hungary at the time, they spoke German. It was part of the Austro-Hungarian Empire, and German was the language for the upper classes, the intelligentsia, etc. He had private tutors, usually two tutors at a time, and that lived with them. And with the tutors and other outside instructors, he was able to learn and be fluent in English, French, Italian, Greek, German, Latin. It was amazing. He was a prodigy who could multiply 8-digit numbers in his head at age 6. That I've seen quoted in different books about him. Some say it was division, some say it was multiplication. I'll left multiplication here, but in general, a lot of the little things about von Neumann with his life, they're written without serious reference. So there's somebody remembered something. So there's differences here and there. He knew calculus by age 8 and Borel theory at age 11. Borel theory was the theory of sets. That's the basis of probability theory. And Borel was a famous mathematician who was one of the founders of serious probability theory. So he certainly had an interesting background. Yeah. He wanted to be called, or he was called János. That was his proper name in Hungary, in Hungarian. And Janci was the nickname, sort of like John versus Johnny. When he was in Germany, which he spent many years in, to get working with Hilbert and doing some mathematics and other work there, he was Johann. In the US, he always wanted to be Johnny, not John, but Johnny. So everybody that knew him called him Johnny. If you read any of the articles written by his various colleagues, they always call him Johnny. He had an amazing memory. It was, the best I can say is near photographic because he didn't recognize people that well. So you can't call it photographic, but He had read a 44-volume history of the world in German, and decades later, if a topic came up that was in the book, he could quote sections of the book about that. And he would get into debates with somebody about Byzantine Empire, and he would point out something that the expert didn't know. The von Neumann children were always encouraged to present interesting topics at dinner. And this was actually common in a lot of families in Europe in those days. They would consider dinner a time to discuss, the issues of the day, whatever somebody found interesting, etc. And they did this regularly. One of the ones that's cited by his brother is at some point he had read that children of various language backgrounds, they seem to learn their own language in the same amount of time. I think it was about 2 years. And so he asked, what is the brain's primary language? Is there something beneath that that's going on that sort of was why it took 2 years for the average student, no matter what the language was, to learn their primary language? Okay, because he wrote in chess in game theory, it's worth noting that he was a mediocre chess player. As brilliant as he was, it's interesting that he wasn't a good chess player, probably because he didn't care enough to try that hard at it. And later on in life, when he's trying to play poker, he was not that good at poker, which is actually what his game theory was more about, poker rather than chess. And at some point, he tried to develop a system to beat roulette in Monte Carlo, and that didn't work either. He wasn't interested in music, and he didn't have interest in sports. At some point, his second wife said, hey, why don't you learn to ski and we can take skiing vacations? And he said, if you want to do that, we have to get divorced. So he had no interest in any kind of sports. Now, a historical note, what's going on in the world at this time. When he was age 11 to 15, 1914 to 1918, World War II was going on, World War I rather. And it was a horrible war with huge battles and deaths, etc. But none of it was near Budapest. The Hungarians were involved because it was the Austro-Hungarian Empire, but they mostly fought on the so-called Eastern Front against Russia further north, and some further south, probably around Serbia. So there was really not much direct impact on him because of the war. He and his brothers and a cousin made up a game. I forget what they called it, but it was basically war games with graph paper, and they would have armies and fortifications and all this, and they would play games. And my guess is that John von Neumann won most of them, but I don't really know. There's no documentation of that I've come across. The interesting thing that happened now is in 1919, at the end of the war, there was a treaty, I think it was the Treaty of Trianon, in which the Austro-Hungarian Empire was broken up. And most of what had been the Hungarian half of the Austrian-Hungarian Empire was given away to other countries, mostly because the ethnic groups there were not Hungarian, but some of the more Hungarian areas. So it went to Czechoslovakia. Most of what is now called Slovakia was part of Hungary before that. Romania, you've probably heard of Transylvania in Romania. Well, that was actually part of Hungary, and they were Hungarian natives. Yugoslavia, that part, Ukraine, a lot of the areas where they're fighting in now were part of the broader Hungary before World War I. The significant thing for von Neumann's history is that in 1919, a Hungarian, Bela Kun, who actually been captured during World War I and was taken back and indoctrinated in Russia in the early days of the Soviet Union. He was indoctrinated actually by communists there. It wasn't really the Soviet Union yet. He came back and had a coup, and for 4 months he took over Hungary. During that time, von Neumann's family had to flee the area because they were taking over properties and things like that. They went to a summer house they had to be safe, but they had enough money and connections that they were able to pay to keep their property protected. So they, 4 months later, were able to go back to the same house that you saw in the picture. But as a part of this, he lived not quite under, but with or near communism and the Soviet Union, still Russia, for 4 months. And he developed a deep hatred and distrust of Russia and the Soviet Union. And a deep hatred for them, along with the hatred of Nazism, which then affected him, in a few years after that, because he was from a Jewish family. And this comes out later in his politics in the post-World War II era and what he was doing then. Okay, what about his education? He went to a high school, which was actually called a gymnasium after the German model, because again, the upper classes spoke German and they modeled their educational system on the German model. We would probably call it a high-end prep school now, maybe like in Eton in England or some of the prep schools in the US. It was very exclusive, presumably expensive, but I didn't say anything that said what it cost. But they had a very strong program in a lot of things, but particularly in math. They went up to calculus and math, which was rare for high school in those days, I think. But John already knew calculus when he went there, so it almost didn't matter to him, but he had very good teachers who identified how brilliant he was. And Ron was speaking to his family, I think, this guy is really smart in mathematics. But that school had a number of famous graduates. Eugene Wigner, who was one of the Martians of science that John mentioned earlier, later won a Nobel Prize, partially based on work he did with von Neumann. Also another Nobel Prize winner in economics, Janos Harvasi. He didn't go to the US. This was like a generation later. He actually got a Nobel Prize in economics for work that he did that was based on game theory. Andy Grove also went to that school. He was the Intel CEO, and I forget what his Hungarian name was, but he changed his name in the US. For those interested in classical music, Anatol Dorate, who was a big star of orchestra leader back in I guess the 50s, the 60s, maybe the 70s. He graduated from that school. And Theodor Herzl, the founder of Zionism, a couple generations before, graduated from this school. So it was one of, if not the most prominent schools in the area. It's called a Lutheran school because it was actually organized by the Lutheran Church, even though most of the students were Jewish. There was no enforced religion that everybody had to follow. There was training in whatever religion you claimed to be. There was a session for the people that were Lutherans. There was this thing for the people that were Jewish. There were a couple of Catholics there. But in every other thing, they were treated equally, and they got a great education. And this is a photograph of the school, again, from a trip about 8 years ago. I tracked down where the school was and took some pictures of it. And there's a plaque there that mentions, from left to right, Eugene Wigner. Now it's got the Hungarian pronunciation and order, name ordering. So Wigner, Jano, Hungarians put the last name first, or we call the last name, von Neumann and Harsani. What they don't mention is that Teller also went there, but those are the three most famous graduates. And the school was shut down for a while during the Soviet year, but was reopened. Okay, so his teachers, was there one particular math teacher who was very prominent at this school, went to his father and said, this guy's really too smart. You need to do more with him than just what we're doing. And he talked to his father, and his father arranged a series of private tutors for him that were all prominent mathematicians. One was Michael Facchetti, and the first paper that von Neumann wrote was with him, or while he was still in high school. Gabor Zago was another one of the private tutors. He's probably the one that introduced von Neumann to formal set theory. He later came to the US and became the chairman of the Stanford University Math Department, so he was no slouch. And the third one, who was the most prominent one, was Fejer, who was a prominent mathematician, possibly the most prominent in Hungary at the time, but I don't really know that for a fact. But from the things I've seen about work that Hungarian mathematicians were doing in that era, it seems like he was one of the most prominent ones. And This is a photo taken actually from 1928, so it was somewhat later. And you can see some of the people that are there. There is Figer, oops. Figer is seen in the photograph. I think he's at the far right over here. I'll mention Tibor Rado, who I think was over here, only because in Al Hayo's talk on the Busy Beaver problem, he mentioned that a lot of the work for that was done by Tibor Rado. So he was also in Hungary at the same time. The other interesting one is George David Birkhoff, who at the time was probably the most prominent American mathematician. So this group that was at a conference, they had very prominent mathematicians both locally and internationally. And Figer was actually not just a prominent mathematician, he was a friend of von Neumann's father, and he often had dinner with them. So von Neumann was very much connected with Figer. Okay, a few more words about Figer because he comes up again later. He worked in something called harmonic analysis, which is part of functional analysis, and I'll show you briefly what those top areas are, but those are very important areas of mathematics. His PhD students included, well, the first two tutors, Fichette and Szego, John von Neumann, Paul Erdős, who is probably the most prominent, the most published mathematician of the 20th and 21st century. I mentioned him already. George Polya, who was a prominent mathematician and then wrote a couple of books on thinking about mathematics, how to attack mathematics problems, not being specific to the domains, called How to Solve It. Those books were very well known in the 60s and 70s, and you might have read some of those. He also emigrated to the US. And there's Tibor Rado, another one of Figer's graduate students. Okay, so Johnny graduated from the Fasori Gymnasium in 1921. So he was 18 at the time. While he was at the university, he spent a lot of his spare time hanging around, actually while he was at the gymnasium, he spent a lot of his time hanging around with the mathematicians at the University of Budapest. That was his real love, was mathematics. Figer was there were other mathematicians that were there. It was the University of Budapest was the center for mathematics in that part of Hungary. There was another center which wound up getting spun off into Romania and they moved somewhere else, but we'll mention that later. So he was hanging around with mathematicians a lot, but they were professional mathematicians, they were researchers, not just the high school teachers. So he was exposed to a lot of math at that time. In his senior year, he started actually publishing. His first paper, which was written while he was still an undergraduate, was co-authored with Fichette, his tutor, and it was called the Zeros of Chebyshev Polynomials. It's a topic in numerical analysis that he never really went back to. Chebyshev polynomials show up in numerical analysis as a better way to approximate functions than something like the Taylor series, but they're much better computationally. But even though his interest was math, his father thought he couldn't really get a good job in math. So his father actually talked to von Karman, who was mentioned as another one of the Hungarian Martians, but was a generation before John von Neumann. He's the one that went off and did a lot of stuff in aeronautics, etc. He actually was a co-founder of Jet Propulsion Laboratories. And some of the things he did designing airplanes went into the design of the plane that dropped the atomic bombs on Hiroshima and Nagasaki. So he's got a connection with the Manhattan Project indirectly. Anyway, so his father talked to von Karman, who was very well known and prominent at that time, and they agreed that what he should do is go into chemistry, which in those days was the big career alternative. Just like in the 60s, if you wanted to go into something scientific but very practical and make good money, you probably went into either chemical engineering or electrical engineering. Now you'd go into computer science or electrical engineering. In those days, it was chemistry. So he wound up going to study chemistry while he was studying math. His chemistry work was started with 2 years in the University of Berlin, which was a prominent school, and he didn't have any chemistry background, so he just did that to learn chemistry, basic chemistry, before he went to chemical engineering. So he was doing that for 2 years, but along the way, he took physics courses, including statistical mechanics from Einstein. So he was doing much more than just basic chemistry. Then he did the next 2 years to get his degree in chemical engineering at ETH in Zurich, which is the school where Einstein got his PhD. And that's the reason why many of you probably heard of ETH. And I'll have a little more about that later, but it's interesting to note that there's a very difficult exam to get into ETH, which John von Neumann supposedly aced. But when Einstein went to go in there, he failed it the first time. So I don't know what that says. Okay, while he was at ETH, one of his professors was Hermann Weyl. It's spelled a while, but it's pronounced Hermann Weyl, who was probably the second most prominent mathematicians in Europe or in the world at that time after David Hilbert. Von Neumann studied Hilbert's work on foundations, mathematics, set theory, etc., with Weyl, and sometimes taught Weyl's classes while Weyl was off on meetings and things like that. Remember, at this point, John was just, Janosch or Johnny, whatever, was just an undergraduate student, and he was taking over for Professor Weyl, the second most prominent mathematician. So clearly he was well ahead of the game in math, even when he was supposedly studying chemical engineering. Weyl, by the way, later went to the Institute for Advanced Studies in Princeton shortly after John von Neumann was appointed to the faculty there in the early 1930s. So they had connections all along. In parallel with doing this work in chemistry and chemical engineering, he was also enrolled at the University of Budapest to study math and wound up getting a PhD there in 1926. He did that without attending any classes there. He just would come back at the end at each semester, take the exams, ace the exam, and then go back to studying what he was supposed to be doing as chemistry and chemical engineering. So that was pretty amazing that he was, in 5 years, did a PhD in one area, bachelor's degree or whatever, I'm not sure what level it was. They never said, so I assume a bachelor's level degree in chemical engineering in cities that were, I don't know, hundreds of miles apart. Okay, now we'll start getting into some of the mathematics that he did. Let me just check the time. Okay. So this part is kind of a repetition of what I talked about in the Gödel talk, but basically mathematicians really around the turn of the century were concerned about the fact that some parts of mathematics weren't working right, and they decided they had to prove things from a more basic level because things were done sloppily without always knowing what the conditions are, et cetera. So there was a move to try to build up all of mathematics from the fundamentals of just set theory and say everything comes out of that. Unfortunately, Bertrand Russell found a paradox that nobody could find a way around, which was something called the Russell paradox. And I won't go into it in any detail. Basically, it said that there's something fundamentally wrong with just assuming you can call anything a set. And a lot of people tried to work to fix that. One of them was John von Neumann. And what he did was do some work on axiomatizing set theory. And what he did is still in use today. Just pictures of the people that are involved. Bertrand Russell on the left, and Whitehead was his partner. They were working together on something called Principia Mathematica, trying to build up everything from set theory. David Hilbert is the one that got involved and very much pushed this kind of an approach and wanted a formal axiomatic system for everything. And he was working hard on that. The bottom left is John von Neumann. The picture says he's in his teens. I'm not sure exactly when it was taken, but that's probably what he looked like around the time he was getting his PhD and starting to work on set theory. On the bottom right picture is one that I love. It shows John von Neumann actually in the late 40s, possibly even early 50s, when he was working on the computer project at Princeton or at the Institute of Advanced Studies in Princeton. That picture, I believe, was taken in what they call the common room common room at the IAS building. And I think the picture behind John, if I recognize it properly, is actually Fold Hall, which was the Institute of Advanced Studies. John, is that correct? The picture in the background of your unmute yourself, John.
I am really not sure.
Okay, because it looks like Fold Hall. And if that is the case, then this picture was taken in the common room in that building. And in the late 1940s, when Neumann was working on the computer, that building would have included the offices for Kurt Gödel and Albert Einstein and possibly Hermann Weyl. I'm not sure exactly what years he was there, but he was there for a while too. So, and that common room is actually still in use today. And if you go to any of the public lectures at the Institute for Advanced Studies, and there are some public lectures, depending on what the lecture is, they will sometimes have a reception in that same common room. Okay, so the ideas for his first three papers on set theory, I'm not going to go through what he actually did, but he basically came up with some ideas for formalizing set theory. The first one was about the cardinal numbers, which there was a talk about Cantor and infinite numbers a few months ago in this group. What von Neumann did is he actually got a solid axiomatization for that. He also did it for what are called the ordinal numbers, which actually are very different. First, second, third, as opposed to 1, 2, 3. His axiomatization of the ordinal numbers is still in use today. And then our third paper was called an axiomatization of set theory. This is where he started getting to the more fundamental things about sets, not just numbers. And he said, the aim of this work is to give a logically unobjectionable, meaning you can't argue with it. This is the right thing. Axiomatic treatment of set theory. He wasn't going to have any kind of contradictions in it, he thought. And as far as I know, none actually came up. I will say something about the difficulties that make such an axiomatization desirable, meaning he's going to say something about the Russell paradox, and there were several other paradoxes. Okay, so he did that work. He actually wrote a letter to Zermelo, who was one of the other people in foundations, in 1923, while he was still an undergraduate, and described this. It eventually became his PhD thesis, and it was integrated into a more proper paper in 1928, but there were 3 papers that came out of that. So that was his main achievement there. And I won't go into what he actually did, which is the first bullet. But in 1926, when he got his PhD, he was given a Rockefeller Fellowship to study under Hilbert in Göttingen, Germany. And Hilbert was the most prominent mathematician at the time. He was the one that was very big on all this stuff about foundations of math. So you would expect this to be spending his time now working on foundations of math. And he did do some work there on foundations, some stuff that was published later, but nothing that as important as the first things. The Rockefeller Foundation actually was funding even a whole school in Germany at the time. Heisenberg had a Rockefeller Fellowship to study with Bohr a year or 2 before this. So the Rockefeller Foundation was actually doing a lot in Europe in the pre-war years. I should also say the pre-Nazi years too. This is in the late 1920s. Okay, the other important part of foundations of mathematics, which is really what Gödel was doing, was Hilbert had a program where he thought mathematicians had to prove 3 things about mathematics to say mathematics really works. One is completeness. Every properly formed sentence in mathematics can be either proved true or false. Second thing was consistency. You should be able to prove that the system of mathematics you work in is consistent. That is, there's no contradictions. Because if you get a contradiction, as with the Russell paradox, the system really has to be considered useless. And the third is decidability, that there is an algorithm to decide if a properly formed sentence is true or false. The first one, completeness, says you can prove it's true or false, but doesn't say you know how to find them. The decidability says you can look at any statement and you can decide, there's an algorithm to decide if a properly formed sentence is true or false. So one says you can, somewhere there's a proof, the other one says there's got to be an algorithm that gets you to that. Hilbert started working on this and stated early in the 20th century. Parts of it were the famous Hilbert problems of 1900, but he restated them again in a talk given in Bologna in 1928. Okay, von Neumann at this point was working with Hilbert, and we'll see he was actually doing a lot of work on the foundations of quantum mechanics also at the same time. And he didn't publish anything then, but people that knew him think that he was actually working on these foundational questions of Hilbert along at that time and into the late 1920s. Unfortunately for him, he thought he was trying to prove the things that Hilbert said we need to prove. In 1930, Gödel presented at a conference that, hey, number one, you can't do. There has to be statements that you can never prove true or false. And number two, there's no way that you can prove the completeness of standard mathematics with the integers from within that system. So the first two things of Hilbert were dead in the water. The third one we'll get to that in a minute. Okay, von Neumann was at this conference, and he listened to the talk, which was put the last day and probably the last talk. People were drifting away already. Hilbert didn't attend the talk, but Gödel, von Neumann listened to the talk and then went and talked to Gödel about it to understand the proof better, because he found it really interesting. He thought it was important, even though Hilbert didn't seem to care about it. He then went off and thought about it, and he wrote a letter to Gödel saying, hey, your talk disproved or showed that Hilbert's first thing doesn't work. I have a way using what you did to prove the second one doesn't work. And Gödel wrote back, said, yeah, well, I know that. It's in the paper. I just didn't bother talking about it. Von Neumann, being a real gentleman, did not say, well, I thought I'm going to publish it too. He said, okay, it's yours, you publish it. And so he never published, even though he came up with it based on Gödel's first proof. He came up with the idea for the second one, but he said, okay, Gödel's doing it first, that's fine, which a lot of people would not have done. And beyond that, John von Neumann was now in Princeton on the faculty of Princeton, I think as a visiting professor. He came back and gave a talk not on his own work that he was doing, but he actually gave a talk on Gödel's work and arranged for Gödel to get an appointment at Princeton. So he was really the gentleman about that. Okay. He never published anything in Foundations again, although colleagues report that he continued working in the area for a long time. I don't know if there's any documentation of that other than what colleagues remember. In 1936, Turing came up with his famous paper that basically said number 3 doesn't work either, can't prove that. And in doing that, he came up with the idea of what is now called the Turing machine. He called it something else, but that later became an inspiration for John von Neumann when building the Institute of Advanced Studies stored program general purpose computer after World War II. Now, the curious thing to me is in 1936 to 38, Turing, who had written the paper while he was still a graduate student, went to Princeton to finish his PhD with a thesis under Alonzo Church. So he was there for 2 years while von Neumann was also in the Princeton area. He was at the Institute for Advanced Studies, but I think at that point, they were still using the math department offices at Princeton for the Institute. So they certainly had a lot of contact. He knew him. How much he knew him, I don't know. It's not well documented. There are reports that he was at some of von Neumann's famous parties in the 30s. Now, this is jumping like 10 years ahead from what we were doing before. And John von Neumann actually invited Turing to stay at Princeton as his math assistant, which he had a right to hire at the Institute of Advanced Studies. But Turing decided he wanted to go back to Cambridge and worked at Cambridge. So the curious question is, they were around each other for 2 years. Did they talk about building computers? Because basically what von Neumann did in building a computer after World War II was implement the fundamental ideas that were in the Turing machine. And he figured out how to actually build something that was a programmable computer out of, based on Turing's paper. So that's an interesting question that we'll never have an answer to. Okay. Now, I mentioned functional analysis earlier. It's an area of mathematics that some of you probably have heard of and know something about, but many of you probably haven't, because it typically only shows up in graduate programs in math and physics, where it's used widely, and some engineering disciplines. But his work on quantum mechanics was important, and it used functional analysis. It's mostly about infinite dimensional spaces, and it's very important in quantum mechanics, PDEs, Fourier analysis. And I just read recently that they're using it in machine learning too, even though they have to have finite dimensions. They're not infinite dimensions, probably a huge number of dimensions. So they're approximating it with functional analysis things. Basically, functional analysis is, instead of having regular analysis, which is as points in n-dimensional space and a notion of distance and limits, the points you have are whole functions. Okay, I'm not going to, you get the slides and I won't go through more of this now. And they have algebraic structure, a sense of nearness, and a basis, which is things that can be used to construct all those points in the space. If you see any of these words, they're talking about functional analysis: Banach spaces, Banach algebras, Hilbert spaces, operator theory, spectral analysis, harmonic analysis, a lot of things in wavelet analysis. All these things are parts of functional analysis. So you might have seen some of these terms. And I'll just mention one example, which is the root of functional analysis, which is something that a lot of you know because it's used in electrical engineering, mechanical engineering, et cetera, is Fourier analysis, the Fourier series. The basic idea is that you can represent the continuous function with the right conditions on a closed interval as an infinite sum of sine and cosine terms. And that is really what functional analysis started doing. They do a lot more with it now, but the idea is that you have this basis of the sine and cosine functions. And in Fourier analysis, you have to understand conditions under which the Fourier series, there's a formula for computing, converges to the function. And you have to be careful about getting all those conditions right. And there were problems earlier on with Fourier analysis when the conditions weren't clearly understood and things didn't come out right. But this is sort of the origin of functional analysis. Okay, so now let's go to quantum mechanics. And how much time do I have? Okay. Okay, in the early 20th century, the physicists will know all the different experiments that showed that at the particle level, things behave strangely. It was not Newtonian mechanics. Sometimes things acted like a wave, sometimes a particle. There were all kinds of strange things going on. And they understood this, and they were trying to develop mathematical models of the atom and particles, etc. They weren't quite there, though. In 1925, Heisenberg came up with something that actually was very good, that matched all the experimental results. It was based on matrix mechanics, and that was a model for quantum mechanics, a mathematical model, and it used an infinite dimensional matrix. Schrodinger at ETH came up with a different model based on wave theory that looked completely different, but they came to the same results also. They didn't like each other's thing. Schrodinger was repelled by the instantaneous quantum jumps of Heisenberg's model. Heisenberg said Schrodinger's model was crap. That's why it's translated in one book, another, it's disgusting. So, but they came up with the right answers. Okay, here's a picture of Heisenberg from about the age he was. He was only 24 when he came up with this model. And on the right is Schrodinger, who was close to 40 at the time. So on the left, you see this infinite matrix. And on the right for Schrodinger, you see this wave thing going around. How could they be doing the same thing? That was the question. Dirac also had another way of approaching things using the Dirac delta function, which mathematicians said, that's crap, it doesn't make sense. Okay, so at this point, Johnny is with Hilbert in Germany. Initially, I think to work on foundations, they started looking at this stuff with the physics, because Heisenberg was also in Göttingen, where Hilbert was, and they wrote one paper together about quantum mechanics, and then Johnny got serious. He was at the University of Berlin by then, and what he was able to do basically is say, those two things really are related, and in fact are equivalent. And what it came down to essentially was that he recognized that it was almost as if the Schrodinger model was the continuous function, and the Heisenberg model was the Fourier coefficients. And he was able to prove conditions that was satisfied, so that was true. So then you could really say there's a relation, just like there's a relation between the Fourier analysis of a function and the coefficients. You can go back and forth between them. And the points in this case were actually in Hilbert space. It's a little more complex than just the simple Fourier analysis, but that basically was what he was able to show. And he did that on the basis of something called the Riesz-Fischer theorem, which was conditions under which a series of numbers could be the Fourier coefficients for a function. It was proved in 1907 by both Riesz and Fischer independently. So this was around, because now von Neumann, we're talking about 1926 or so. So it was like a 19 or 20-year-old theorem in an area that was not related to any of the work that von Neumann had been doing. How did he know about it? This is an interesting question. I came up reading some details about this area and putting this talk together. I said, well, how did he know about that? He should have known about logic. Where did he get off on this stuff with the Fourier analysis? Well, my speculation, and I don't know if anybody has written about this, is that von Neumann, when he was at high school, he used to hang around with the math professor there. I mentioned that earlier. Some of the professors there, particularly Vegère, were prominent in functional analysis. So he would have had exposure to that. In fact, Vegère, his mentor, and Riesz, of the Riesz-Fischer theorem, he was a close associate. They were both co-advisors on 4 dissertations, including Tibor Rados. It comes up again. Al, I'm glad you mentioned him earlier because I hadn't heard of him before this. Also, Hermann Wey at ETH, when von Neumann was there, was also working in this area as well as the foundations of math. So somewhere along the line, von Neumann was hanging around with mathematicians, absorbing what they were doing, and learned enough of it that he could go to a physics problem and say, wait a minute, I have the math to solve your problem. And it's another of many cases in history where mathematics was developed for something else, and the scientists needed some kind of mathematics, and the mathematicians got involved and said, hey, here's the math. It already exists. You don't have to develop it from scratch. And here's this picture again. Notice Riesz is in the top left corner. He's the Riesz-Fischer theorem. So that's just another connection. The conference was at Szeged University, which is about maybe 50 or 70 miles from Budapest. That was the university where a lot of faculty came when this part of the Hungarian Empire was given to Romania. There was a school of mathematics. They just came to Szeged University, and they worked a lot with the people in Budapest. Okay, so von Neumann published. Let me just see how I'm doing time-wise. We're gonna be close, but not quite. Published 3 papers on quantum mechanics in 1927 alone, with the equivalence of the Heisenberg and Schrodinger models proven. The physicists were free to use either one. You could use either one, whichever was worked the best for you. So in some situations, one you could use one, some of the others. In fact, they were doing that before the equivalence even proved. Schrodinger even used Heisenberg even used the Schrodinger model for some of his computations, even though they weren't proved to be the same, and he thought it was garbage. Okay, skip the next one. You can read that later. There was just another model that Dirac came up with. Dirac was a brilliant, intuitive physicist, but his math needed help. And in fact, in 1940s, someone else, Laurent Schwartz, came up with a way to fix the mathematics in Dirac's model, and he won a Fields Medal for that, which is one of the 2 top prizes in mathematics. Later, Richard Feynman came up with another way of doing it. It's called the Feynman diagrams, and quantum mechanics people actually prefer to use the Feynman diagrams now, but they're all equivalent. Okay, another important question that came out of von Neumann's work is something called the hidden variable problem. The results of quantum mechanics were probability distributions, and people didn't like it being a probability. You didn't know where an electron was. You had a distribution of where it might be until you observed it. Once you observed it, then it was pinned down to it. But there's something random that people didn't like, especially Einstein, who said, God does not play dice, blah, blah, blah. You've probably seen that quote. And what a lot of people, including Einstein, thought was that there's another layer of physics that they haven't developed yet that's even lower level than quantum mechanics. And in that, there was the variables there would have had deterministic results that when you bring things together, it looks like it's random, but it really isn't. So that's the hidden variable problem. What are the hidden variables? How can we get to another level down and say, this is really deterministic. We can go back to the world being deterministic, and it's wonderful. An example of a hidden variable problem, just so you can get an idea of what they meant by that, is if you're tossing a single die, it looks like the result should be a random distribution of the values from 1 to 6, 1/6 for each of them. If it's a fair die, maybe it's not fair, it'll be a little bit different, but it's probability distribution. But if you go deeper down, if you know the exact position, orientation, speed, direction, all the bouncing conditions, etc., of a toss, if you just could capture all that information and had it completely accurate, then you could use Newtonian mechanics to actually say whether it's going to come up at 1 or 6, whatever. Now, nobody even now could actually capture that in enough detail for somebody holding a die and tossing it. Maybe if you had some controlled experiment where you could control what things were, you could do the computation, but it's very, very hard to do. But that would be a hidden variable. So it's not really random. There is physics behind it. What John von Neumann was able to prove as part of his work was that there could not be a hidden variable. And that is still a little bit of a controversial thing in physics, but it's very important because that's if you take his proof to be true, which most people do, that the world really does have this random element in it, and there's no way of getting rid of it. Okay, so he used an axiomatic approach to building up the mathematics of quantum mechanics and put it on a firm mathematical basis. There were all kinds of fudge things that were done in both models earlier on, even though the instinct was work. This should be like Dirac and the delta function. This should work, and later the mathematics was cleaned up. But von Neumann cleaned it up for the Schrodinger and Heisenberg models and showed that they really were equivalent. And he actually treated it as an axiomatic development. He eventually put the work together in a book, The Mathematical Foundations of Quantum Mechanics, which came out, I think, in 1932 in German, was translated to English, and it's still available in English. The new edition was published in 2018 by Princeton University Press. So if you want to read The Mathematics of Quantum Mechanics, there's a book that you can get on Amazon that describes it all, and it's basically what von Neumann did. And actually, it is his book. It was translated to English, and things were made clearer, supposedly. I haven't tried to read it. I don't know enough physics to read it. And von Neumann continued to work on quantum mechanics for the rest of his life, but mostly in the late 1920s and 30s, actually. The mathematics he used included Hilbert space theory, spectral analysis, eigenvectors, which is a concept from Hilbert spaces, and other topics in what's now called functional analysis. Okay, the summary, just so you can see how compressed time frame he did so much. In 1921, he graduated from high school, published a paper. 21 to 25 and 26, he got degrees in 2 different areas in 2 different cities that are far apart. All the stuff for his PhD thesis, he had described in a 1923 letter. So while he was still an undergraduate in 2 different universities in 2 different areas. So that basically was there. The rest of what he did in that was just cleaning up the papers. In 1928 to 29, he wound up publishing 9 papers in foundations, but the first 3 were the important ones. He had in 26, he had a Rockefeller Fellowship to study under Hilbert. 27 to 30, he was in math at in University of Berlin. And 1930 is when he started a part-time position at Princeton University and went back and forth a little bit and eventually came to Princeton full-time. And he had his first 3 papers on the mathematical foundations of quantum mechanics, one of them with Hilbert. In 1927, he was only 24 years old. And 1928, by the way, while he was doing all this stuff in foundations and in quantum mechanics, he wrote a paper that invented more or less the game theory. I mean, there were things like that were around, but he organized and got it straight and proved some major results that there have to be solutions to certain kinds of games. That'll be in the game theory talk next session. And the book on the mathematical foundations of quantum mechanics. So all this happened in 10 years. He made major things in 2 different areas that has major impacts in mathematics. He invented game theory, which then had a major impact in the 1940s when he was at Princeton. He started working with Oscar Morgenstern on theory of games and economic behavior. That's when it started really getting useful. So that was my conclusion of the talk, and I think I just about made it in time. I will stay on for Q&A for those who can stay on. And at this point, I sped through things, I skipped some stuff, but I will have the slides sent out hopefully sometime tomorrow. I have to get it done tomorrow, which has several other things scheduled, because the day after I'm going to be out of town for 2 weeks. So I'm going to try to get the slides and maybe some more references out to everybody. The next session will cover basically from the 1930s through his death in 1957 or 56. And the things that I will be highlighting there is the work that he did during World War II on various topics, including theory of explosions and shock waves and things like that. But most importantly, the work on the atomic bomb, working on the mathematics behind how to do the implosion bomb. And then after that, work related to the hydrogen bomb with Teller and various other people. That's one topic. The other topic will be game theory. And the third I will talk about is his public image, because he became fairly well known in the 50s. He's not known now, but in the 1950s, he became fairly well known. And it's considered by some to be one part of the model for Dr. Strangelove in Kubrick's movie. Kubrick claims there was no model. Wikipedia says the model was 3 people, as a combination of Werner von Braun, Teller, and somebody, Kahn, who worked at Rand Corporation, that actually wrote books on the theory of sort of using game theory and nuclear deterrence and policies and things like that. I think von Neumann fits there very well too, and I would put him there in place of Teller. If nothing else, he was more well known than Teller. It's, you know, what inspired the part was who Kubrick knew about. Yeah. And von Neumann, actually, I look at the New York Times. If you look historically in the New York Times, there's dozens of articles about John von Neumann, including an long obituary when he died. There's articles about him getting appointed to jobs with the federal government in nuclear energy policy, working with Rand, working on doing some things about ENIAC and his computer. So he was fairly well known. And there were, in 1957, when he died, Life magazine had like a 5 or 6 page spread about him. And if you remember, Life magazine was a major magazine, that was quite an occasion to have a 5 or 6 page spread about a mathematician. I don't think any other mathematician ever got that kind of treatment from something like Life magazine.
Yeah.
So, plus, in his last years, he was in a wheelchair because of cancer. And there is a photograph of him getting an award from President Eisenhower in the White House, and he's in a wheelchair. So the fact that he was in a wheelchair was also known. And remember Dr. Strangelove, he was in the wheelchair.
Yeah.
The one thing that was never be connected to von Neumann is that Nazi salute that he would periodically do. That I cannot imagine von Neumann doing. He left Germany, and he predicted when Hitler came to power that within 2 years, Germany, which was then the most important place in science, in physics, in mathematics, he said that'll be destroyed in 2 years, and it was. And fortunately for the U.S., a lot of those people moved to the U.S., including the Martians of science. So at this point, I'll stay open for questions as long as people are interested. And I guess
Well, I'd like to, I have a question, if I may. First of all, thank you so much, Bill. For a non-math major to get into John von Neumann is a really high mountain to climb, and you're helping here greatly. So my question is, when one tries to develop axiomatization for a math theory, I think of it as like building blocks. How do you know when it's complete?
Well, usually you have some context in which you're trying to work. And if there are things that you haven't covered that out of the axioms, that means there's probably another dimension that you need to look at, and you maybe have to add more axioms.
Okay.
And axiom systems can change. They're not locked in stone. But what they are is a base that you can say, from which you can say, okay, these are the things that I can prove from that are true as long as the axioms are true. I mean, the axioms are things that you can't prove. There's just a few things you said, this is, it's obvious, it's got to be true, but I can never prove it. So you want those as building blocks. And if there are things you want to get to that the axioms don't get you to, maybe say, well, okay, I never thought about this. Maybe we need to make an assumption. And the assumption becomes an axiom, and you have to play with it a lot and see if it really works, and hopefully don't find contradictions, because that will kill anything. And the one example that I can think of is a little bit esoteric for a non-mathematician, but there was something called the axiom of choice when they were starting to develop axiomatic set theory. The axiom of choice was thought to not even be needed. Nobody even considered it. And what this says is that basically, if you have any collection of sets, and particularly an infinite collection of sets, you have S that has one element from each of your collection of sets. Now that seems like it should be trivial. I mean, is that true? Why not? But Zermelo, who we mentioned earlier, he actually said, wait a minute, you're making an assumption that you can do that. How do you know you can do it? This is an infinite process. And so that became Zermelo's axiom of choice, that he added that as an axiom, because in a lot of things in mathematics, particularly in a lot of examples I know in functional analysis, you have to be able to do that. And then it became an open question among mathematicians. Okay, do we take this as an axiom? Because we got to state it at least. If we're going to do it, we have to state it as an axiom. And is it really true? And that was examined a lot by Gödel and other people. And in particular, they wanted to compare that with other potential axioms. Another one was the continuum hypothesis, which I believe was mentioned in the talk about Cantor. It should have been mentioned there, which has to do with how many levels of infinity there are and what can be between what. Is there levels in between when you do the infinite sizes as Cantor was doing? And Gödel actually proved one way that you couldn't derive one from the other, and then in the 60s, somebody proved the other way, so that they know that the axiom of choice and the continuum hypothesis are independent. So you could have, it doesn't matter what happens to one of them, it's not going to affect the other one.
Yeah.
And that was considered a major result in the 60s. That was Cohen's result. The second, Gödel did half and then Cohen did the second half. Well, that's the kind of thing, if typically if you feel trying to using something intuitively that you hadn't even thought about. And a lot of exact axioms up at a higher level were things that, it's obvious. And people didn't think about it. Then they realized, well, you're really doing something else. Like the other famous example kind of like that is in Euclidean geometry, which is the first axiomatic system, which still holds today. And there were questions eventually in the 1800s about, well, if this parallel postulate 5, there's only one line parallel to a given line through a given point. So maybe that's not true. And so other models of geometry, including Riemannian geometry, that was later used by Einstein, based on changing that assumption to, and there were a couple of different assumptions. So Riemann did one. There was another version of non-Euclidean geometry that went in a different direction, changed that parallel postulate to something else that was actually done by Bolyai, who was a Hungarian mathematician. And in fact, the Hungarian prize for mathematicians is the Bolyai Prize, named him, but he was like 50 years before von Neumann or something like that. So it's a very good question, and it's something that mathematicians have really thought about. But most people don't work from an axiomatic perspective. You basically use the axiomatic perspective to get to a base level of standard things, that might be about, enough to do calculus and then differential equations, et cetera. And then you just, have things, you make sure you're careful about proving and having initial conditions and all the boundary conditions, et cetera, organized and properly identified. Okay, any more? I see some hands raised.
Bill, if I may make a comment, first of all, thank you for an awesome talk. Do you think that a PhD student today knows all of the mathematics that John von Neumann created?
I doubt it. Mathematics has become very compartmentalized.
I was also going to make a comment that if you're related to Bill's comment that if your axiomatization is capable of simulating a Turing machine, then I suspect it can't be sound and complete. It'll have undecidability problems.
Yes, probably. I would like to add one thing about the work he did on quantum mechanics. All right, so that von Neumann identified this relation between essentially a stronger, a broader version of Fourier analysis, and that could be used. I did find in one book, they said that Schrodinger had identified that correlation was true. That was one of the first books about von Neumann. It was the McCrae biography, and he was not clear about his sources. And he didn't mention this one source he cited doesn't even mention von Neumann. So I suspect that he was just jumping to a conclusion. The thing that I mentioned about specifically relating it to the Rees, whatever his name, theorem, which was from 2007 or 1907 rather. That was actually in the most recent biography of von Neumann. I have to go back and check and see what the site, what he has, because he has very good references in there for that particular aspect. That reference, but he references that specific theorem. That's the only place in the books and articles I've read that mention that specific theorem. But it is the most recent biography that I know of, and it is in the list of references. Any other questions?
And Bobby has a question, I believe.
John von Neumann, it seems like experimentation and mathematics went hand in hand of all his work. And so he was not just theorist, he was experimenting. You think that's how a lot of things came about, because he was experimenting as well as theorizing?
I don't think he actually did experiments. He was basing things on experimental results that other people had. Like, even Schrodinger and Heisenberg, I don't know that they actually did experiments themselves, but they were combining the results of various experiments. So he was a mathematician who was a theorist, where the theory was based on the results of experiments. During World War II, when he was doing things about explosives and modeling explosives, he did actually request that certain experiments be run on explosives. But he was sitting in Washington, working in a secure location in Washington, and sending letters to people at Aberdeen proving grounds and to the Navy saying, "Okay, I want you to run an experiment doing this, this, and this," and he wanted the results, so he could build up his models based on experimental evidence.
Thank you.
So I have another question. John, you have your hand up.
Go ahead, Bill.
Okay. I was reading somewhere that I think Van Neumann said, when you think of languages, verbal languages, they are just matters of chance. I mean, there's nothing fundamental about the structure of a language. It's just kind of people came up with them, and there are many of them. And he felt that math is the same way, that there's nothing to say that we will not in the future come up with another foundation of mathematics. You have any thoughts on that?
I haven't heard him saying that, but I think if you have some area of mathematics, you're not going to come up with another theory that gives different results.
That's true. Yeah, that's true. But you could do it in a different way.
You can certainly do things different ways. Like you could do, in the case of the quantum mechanics, you could do wave version or matrix version. So you can certainly do things different ways, but that's not, and mathematicians often do that. They like to transform problems from one domain to another if you can prove an equivalence. But you're not going to come up with a different direction and get different answers without doing something wrong. And maybe both of them. And there's still a debate among mathematicians about when you have new work in mathematics, new theories, does the mathematics exist and the mathematician discovers it, or does the mathematician invent it? That's a long running debate that goes back at least 100 years, and it's still not settled. And I don't think it ever will be settled.
Well, I think the context of what I read was that a young mathematician has two paths they can follow. One is they can try to tweak some existing theory and extend it and go, but the other, which is much more difficult, because if you do something in an existing theory, it'll get a lot of attention. But if you try to go back and start from scratch, that's another path, but it's much, much more difficult to succeed at.
I'll agree with that. It's also much harder to get a PhD that way. A lot of PhDs are minor variants on work that's already been done.
Yeah.
And in fact, a good advisor is somebody who has an instinct for how you can expand something, modify something, and get new results that are publishable and interesting, but probably not earth-shattering.
Mm-hmm. Mm-hmm. Right.
Okay.
Bill, I was going to make a comment that it's very easy to show that there are an infinite number of ways of expressing any given algorithm. So I suspect that you can have an infinite number of ways of formulating a problem, and what lives long afterward is you find an abstraction for a problem area that's useful and becomes widely used. So what von Neumann did was he found many axiomatizations that were useful and became widely used. I can invent some very esoteric abstractions that probably may be useful for solving problems, but will not be widely used. So if we're looking at natural languages in particular, certain natural languages seem to strike an affinity with people and they become widely used. Then there are all sorts of languages you can invent, artificial languages that just don't catch on, like Esperanto.
Mhm.
I would, in mathematics, a lot of mathematics, it what's called pure mathematics, that doesn't have a specific goal of trying to solve some problem, just explore new directions. That only became somewhat in fashion a little bit in the 1800s and then more so in the 20th century. But what wound up happening is people came up with ideas and started doing things without having a goal, and then somebody found an application for it, and whoa, we never thought of it. And they go back and they find the mathematics already existed. The best example of that is Einstein and general relativity. Riemann and Bolyai and others who were doing this, non-Euclidean geometry by playing with the fifth postulate. Not Riemann, such as Bolyai and Lobachevsky, who took different approaches to that. They were ridiculed. It's like, this is bullshit. It's not the real world. And even Riemann's approach was not the real world that they knew. But it turned out that this abstract mathematics wound up being really useful in quantum mechanics. The same thing could be said about group theory. Group theory was originally invented in the early 1800s for one particular problem. And it doesn't matter what the problem was. And it had limited use beyond that. But over time, it was developed and developed more and more and more when people thought it wasn't useful. But let's see what happens. And then all of a sudden, quantum mechanics comes along, and they started using group theory and symmetries from group theory in quantum mechanics. It became a very important part of quantum mechanics. It also later became an important part of cryptography, as did number theory, which traditionally was thought of as being the ultimately useless piece of mathematics. Hery wrote an essay, A Mathematician's Apology, basically saying pure math is an art and it doesn't have to be used. And in fact, if it's used, it's implied it was sullied a little bit, especially if it's used in anything having to do with warfare. And his example was number theory, the queen of mathematics. You could prove all these interesting theorems about prime numbers and prime number distribution, all these strange things that had no practical use. Well, then along comes cryptography, and you are using number theory in cryptography every time you get on the web and get a secure link. RSA is based on a number theory problem, as are other cryptography. So, mathematics, and it's great that this stuff is already there, because I don't know whether RSA or actually before them, the others who've worked in the area would have come up with the mathematics. It's certainly. I don't think RSA would have come up with that mathematics in any short period of time, because they wanted mathematics that had certain properties, and they found this one that did. But you should go back and read Hardy's essay, A Mathematician's Apology. You can find it online. It's a little bit long, but he talks about pure math, and math is beautiful, and it doesn't have to be useful. In fact, if it's used in warfare, it becomes solid and dirty math. So would have been nice to know how we would have reacted to using it in cryptography for military messages.
So I have one other question I'd like to ask. A lot of Van Neumann's work in his first 10 or 15 years were all in German. Unfortunately, I don't speak German. Do you have any ideas on, can you get a German paper and then a translator into English and do anything with it?
Well, I think a lot of the major things have been translated. Certainly, the quantum mechanics book has been translated.
Mm-hmm. Mm-hmm.
That was translated. It took several years, but eventually that was translated. Now, once you have that book, the papers before that probably don't matter that much. The work he did later, once he came to the U.S., the stuff was mostly written in English.
Mm-hmm.
And in trying to trace down some things for this talk, there are a number of websites that actually have lists of all of his publications. There's a remembrance of him by Stan Ulam, who was his longtime friend from Eastern Europe. And he has a list of 120 or 140 papers at the end with their original titles. And until everything up to 1930 was in German. After that, English started coming into more of them. But anytime he was working with a German, they wrote the papers in German. But by the mid-30s, they were all in English.
Mm-hmm.
I suspect that you could find translations of the most important ones.
Okay, I have a question. Did von Neumann collaborate with any of the theoretical physicists to actually create theory? You mentioned that he worked with Wigner.
Yes.
And as a follow-up of the question is, did he have a favorite physicist he liked to work with?
Well, Wigner was his friend from Budapest. They went to the same high school, 1 year apart. They were very close in Budapest, and then in Germany, Wigner also moved to Germany and did research there because that's where all the good physics was going on. I don't think he had a favorite one except Wigner, because Wigner was just his friend, and they were at Princeton together for a number of years. Wigner was in Princeton University, and von Neumann was a mile away at the Institute for Advanced Studies. And I'm sure they kept in touch a lot. There were, I forget, at some point I counted 6 or 9 papers they wrote together about quantum mechanics over the years. Now, who did what is hard to say. My guess is that Wigner had the theoretical ideas, and von Neumann figured out how to do the mathematics for them. And Wigner's Nobel Prize is based on some of the work that was done with von Neumann.
Okay, thank you. I think there's no more questions.
Okay.
So I would like to thank Bill for the wonderful talk. And please remember, this is part 1. We will have a part 2 in March. And I will send the notice about a week before the talk, just to remind everyone to come. But I'd like to give Bill the old God salute.